Hey everyone, welcome to this, our last review video, and hopefully the shortest one as well. This deals with everything after our most recent exam, so it's section 5.5 in chapter 7. So 5.5 deals with area bounded between functions. So we're given something kind of like this, and we want to find this highlighted area here. So we have these two functions f and g, they intersect at x equals a and x equals b, and we want to find the area bounded between them. And the way we can do that is we set up an integral from a to b, the places where they intersect, of f minus g. Why does this work? Well, if we just find the area under the curve f, it looks a little something like this. And if we just find the area under the curve g, under the line g, it looks a little something like this. And so if we take the difference of the two, we end up with just this purple highlighted region. So you might be asking, why do I have these absolute value bars? Well, it's because if we end up taking the integral of the lower function, here g, minus the bigger function, here f, so if we were to take the integral of g minus f, we would end up with negative this area. So we'd have the exact same number, its sign would be wrong. So it'd be negative instead of positive. And that's why we throw the absolute value bars on here. It just says whatever answer I get, just flip it positive, we're good to go. The other way you might see something is there might be multiple points of intersection. So the two functions might intersect at a, b, and c. And so what we do is we just break the integral apart. We break the area into two smaller areas that we try to find. So we find the area here, the integral from a to b of f minus g, we throw that in an absolute value to make sure it's positive, plus the integral from b to c, we throw that in an absolute value, make sure it's positive. It's really important we throw both parts in the absolute value, because otherwise sometimes we could even end up with an area of 0 if, for instance, we have a nice symmetric function here where this area is equal to this area but is the wrong sign. So we have to treat each part separately, make each part positive, and then sum all the parts together. So let's see an example like this in action. Let's find the area bounded between f of x equals x squared minus 4x plus 3 and g of x equals minus x squared plus 2x plus 3. So step one is we're going to set f equal to g. So we're going to have x squared minus 4x plus 3 equals minus x squared plus 2x plus 3. Okay, and let's go ahead and move everything over to one side so we can subtract a minus x squared plus 2x plus 3 from both sides. And we'll end up with 2x squared minus 6x equals 0. And then from here, we get that we can factor out a 2x from everything. And so we have x equals 0 and x equals 3. So those are our bounds of integration. So now all we need to do is set up the absolute value of the integral from 0 to 3 of f of x minus g of x dx. Now, what is f of x minus g of x? We already found it. And we found it, we got this. How do we know that that's f of x minus g of x? Well, we started here with f of x on this side, g of x on this side. We subtracted g of x from both sides, g of x being, minus x squared plus 2x plus 3, and it worked out to be this. So this is f of x minus g of x. So we already kind of took care of that step. Now all we need to do is plug that into our integral. And now we can take an antiderivative. We have the absolute value of 2/3 x cubed minus 3x squared, evaluated from 0 to 3 in an absolute value. Now, one thing to note here is this evaluation sign and the absolute value look really similar, right? They're both just vertical lines. So make sure to keep track of that in your head and don't get confused. One of these is an absolute value, one of these is an evaluation. If we plug this into our evaluation, or if we evaluate this, I should say, we end up with the absolute value of 2/3 times 3 cubed minus 3 times 3 squared minus 2/3 times 0 cubed minus 3 times 0 squared, all in an absolute value. And this gives us the absolute value of 18 minus 27 minus 0. This is the absolute value of -9, which gives you +9. So this is why the absolute values are important. Area bounded between curves is always positive. So with any luck, that made some sense. If it didn't, we're going to see another example right now, and hopefully that'll make more sense. We want to find the area bounded between f of x equals 3x cubed minus 3x and g of x equals 0. So step 1, of course, is we're going to set f equal to g. So 3x cubed minus 3x equals 0. We can factor out a 3x from both sides. We have x squared minus 1 equals 0. This is another difference of squares. X squared is a square, 1 is a square. So this breaks apart to x plus 1 times x minus 1. So this tells us that either x equals 0 or minus 1 or 1. So we have 3 bounds of integration. So we need to set up 2 integrals. One from -1 to 0 of f minus g in absolute value, plus an integral from 0 to 1 of f minus g. Those are 2 integrals that we need to set up. I may have said 3 earlier. I didn't mean 3. I meant we need to set up 2. So what is f minus g? Well, g of x is 0, f of x is this, so f minus g is 3x cubed minus 3x. So you have an absolute value of the integral from -1 to 0 of 3x cubed minus 3x dx, plus, and I'll use a different color here because I'll solve these separately, plus integral from 0 to 1 of 3x cubed minus 3x dx, all in absolute value. So let's focus on this left one, this one in black here, and I'll solve it first, and then I'll move on to the right one. Let's take an antiderivative. We're going to get 3/4 x to the 4th minus 3/2 x squared, evaluated from -1 to 0, all in an absolute value. This gives us 0. If I plug in 0 here and here, I'm going to get 0, right? So we're going to have 0 minus 3/4 times -1 to the 4th minus 3/2 times -1 squared. And this is all in absolute value. And so this works out to be the absolute value of -3/4 plus 3/2, which is 0.75 or 3/4. So that's half of our thing. Now we just need to figure out this area here. So let me switch over to red. We have the integral from 0 to 1 of 3x cubed minus 3x dx in absolute value. So this gives us the absolute value of 3/4 x to the 4th minus 3/2 x cubed. Oh, this looks kind of familiar. And that should be an x squared. Sorry, not an x cubed. Evaluated from 0 to 1 in absolute value, which gives us 3/4 minus 3/2 minus 0 in absolute value. This gives us the absolute value of -3/4, which is 3/4. Now we sum these together. We have 3/4 plus 3/4. This gives us 3/2 for our total area. This goes to show why it's important we put each part in absolute values. Because if we didn't, then this part ends up being +3/4. This part ends up being -3/4. And if we were to add those together, we would get 0, which is definitely not the right answer. The right answer is 3/2. So we break it into multiple parts. We make each part positive and then add those parts together. Finding area bounded between curves can be really helpful in business because it helps us compute producer and consumer surplus. So if we look at this graph here of a supply and a demand curve, they have this point of equilibrium, point of intersection, equilibrium point, x naught comma p naught. These are kind of special when it comes to supply and demand curves. This area here in gray is called the consumer surplus, and this area here in blue is called the producer surplus. To compute the area in gray, what we're going to do is we're going to take an integral from 0, here this point is x equals 0, to x naught of this function, of the demand function, minus p naught. So consumer surplus is the integral from 0 to x naught of demand minus p naught. And this kind of cyan color here, if we want to compute the area, this producer surplus, again, it's an integral from 0 to x naught of p naught, this higher function, minus the supply curve. Okay, so let's take a look in action. For a certain product, the demand function is given by p equals 42 minus 0.015 x squared. And the supply function is p equals 0.01 x squared plus 2. And we want to find the consumer and producer surpluses. So step 1 is we need to find this point x naught p naught. So to find the point of equilibrium, we set the two things equal to each other. We set supply equal to demand. So 42 minus 0.015 x squared equals 0.01 x squared plus 2. This works out to be, let's see, 40 equals 0.025 x squared. So then x squared equals, and I have to break out a calculator here, 40 divided by 0.025, 1600. So then that tells us that x has to be 40. So our x naught is 40. Let me exit out of that calculator right quick. Our x naught is 40. To find the right p naught value, we just plug x naught, the value we just found, into one of these functions. So then p naught is 0.01 times 40 squared plus 2, which, pardon me while I break out a calculator, 40 times 40 is 1600 times 0.01 is 16 plus 2 is definitely 18. So p naught equals 18. So now we can find our consumer and producer surpluses. Let's remind ourselves the consumer surplus is the integral from 0 to x naught, which in this case is 40, of demand. Our demand function is 42 minus 0.015 x squared. Our demand function minus our p naught, which is 18. Okay, we can simplify this a little bit to get that consumer surplus. It's the integral from 0 to 40 of 42 minus 18 is 36, I think, but no, it's not. It's 24, and that's why we have calculators. So 24 minus 0.015 x squared. Now we can take an antiderivative and evaluate. An antiderivative is going to give us 24x minus 0.015 over 3x cubed, evaluated from 0 to 40. When we evaluate this, we plug in the bigger number. We subtract off what we get when we plug in the smaller number. So we get 24 times 40 minus 0.015 over 3 times 40 cubed. And now let me break out a real calculator. Well, I say a real calculator, a Desmos calculator, one that I can type fancier things into than the Microsoft like 4 function. 24 times 40 minus 0.015 over 3 times 40 cubed is going to be 640. Now, you might be thinking we only plugged in the first number here, and you're kind of right, but it's because if we plug in the zeros here and here, we just get 0 for everything. So our consumer surplus is 640. To find producer surplus, remember producer surplus is the integral from 0 to x naught, which we found to be 40, of p naught, which we found to be 18, minus our supply function, which is 0.01x squared plus 2. Okay, one thing to note is we're putting the entire supply function in parentheses, okay, because we're subtracting off the entire supply function. So we can rewrite this a little bit to give us the integral from 0 to 40 of 18 minus 0.01x squared minus 2, which is definitely the integral from 0 to 40 of 16 minus 0.01x squared. So now we can take an antiderivative and evaluate. So we get 16x minus 0.01 over 3x cubed, evaluated from 0 to 40. This gives us 16 times 40 minus 0.01 over 3 times 40 cubed minus 16 times 0 minus 0.01 over 3 times 0 cubed. So that's just 0. Let's compute this, and I'll plug this into Desmos right quick. We're going to have 16 times 40 minus 0.01 over 3 times 40 cubed gives us 426.67, I'll call it. That is our producer surplus. So that's area bounded between functions. After that, we moved into Chapter 7, which is all about multivariable functions. And 7.3 is a pretty quick and easy section. It's all about just plugging numbers into multivariable functions and understanding what f of xy means. So essentially, if we have a function f of xy and we want to calculate f of 2, 3, we essentially just copy and paste a 2 anytime we see an x. So because 2 is in the first coordinate, and the first coordinate corresponds to an x, anytime we see an x, we plug in a 2. And because a 3 is in the second coordinate, and a y is in the second coordinate here, anytime we see a y, we copy and paste a 3. So for example, production can be modeled by f of xy equals 100 times x to the 0.75 times y to the 0.25. This is called a Cobb-Douglas function, if you might remember from section 7.3. What we want to do is compute the production level when x equals 1500 and y equals 1000. So we just plug in 1500 for x and 1000 for y. We write f of 1500, 1000 equals 100 times 1500 to the 0.75 times 1000 to the 0.25. And again, I'm going to need to break out a calculator here because I can't pretend to do that in my head. Well, I guess I could pretend. I just don't think I'd be very accurate about it. And we get an answer of 135,540.3. Now, typically, when it comes to production, we tend to round down, right? Because we can't produce 3/10 of a unit, so we tend to round down to just 135,540. That's section 7.3. That's probably all the time I'm going to spend on it. 7.4 is all about partial derivatives. I understand some of y'all are having a little trouble, so what I'm going to do is I'm going to attach some other videos made by other people that I think do a good job of explaining why partial derivatives work the way they work. So I'll skip that for now. And then we moved on to the very last section that we're going to cover, section 7.5, which is all about maximums, minimums, and saddle points of multivariable function. And we introduced this new concept, this function d. It's called a Hessian, and it's complicated. But essentially what we need to do is we need to find 4 partial derivatives, 4 second partial derivatives, fxx, fyy, fxy, and fyx. And we throw them all together into this thing here. And then we also need to memorize this kind of table of results. So if this d is bigger than 0, and this fxx is also bigger than 0, then xy is going to be a relative minimum. If d is bigger than 0 and fxx is less than 0, then here we're going to have a relative maximum. And if d is less than 0, then we're going to have a saddle point. But how do we find these special values? What are the critical points of a multivariable function? Well, to find the critical points of a multivariable function, we set both the first partial derivatives equal to 0. In the same way, when we're solving for maximums and minimums of one variable functions, we set the first derivative equal to 0. We're doing the same thing here, but we have two first derivatives. So for example, let's say we wanted to find the maximum, minimums, or saddle points of this function here. F of x comma y equals x cubed minus 3xy minus y squared. Step 1 is we need to find the partial derivatives, the first partials. F sub x. When we're taking first partial derivatives, one way you can think about it is if we're taking the partial derivative with respect to x, we're going term by term, and if we see an x, we apply our standard power rule to that, and if we don't, we send it to 0. So here's what I mean. This first term has an x, it's an x cubed, its derivative is 3x squared. Minus, this term has an x. If we apply our standard rules to just the x, we just copy and paste everything else as it is. We have 3 times, the derivative of just this x is 1 times, and then we copy and paste that. Minus, and then this thing doesn't have an x in it at all, so it just goes to 0. Okay, and 3 times 1 times y, we can simplify that to just 3 times y. F sub y. This first term doesn't have a y in it, so we're good to go. It goes to 0. Minus 3 times x times y. It's a constant times y. If we apply the rules of differentiation just to y, its derivative is 1. So we copy paste everything else times the derivative of the y term. Minus, and then here if we take the derivative of just this y term, we're going to get 3y squared. But 3 times x times 1, that's just 3 times x. So let's just write 3 times x minus 3y squared. So these are our two first partial derivatives. Now what we're going to do is we're going to set these both equal to 0. Okay, and we're going to solve. Let's see. I'll take this equation here. This tells us that 3x squared equals 3y. So then x squared equals y. Now we have a nice substitution we can make. We can substitute that into here. We get minus 3x minus 3 times x squared squared equals 0. So minus 3x minus 3x to the 4th equals 0. We can, first of all, we can kind of move everything to the other side to get us something positive. We have 0 equals 3x to the 4th plus 3x, just because in general I think it's easier to work with positive numbers. And now we can factor out a 3x. And this gives us x cubed plus 1. All right, so this 3x here, since this whole thing equals 0, this tells us that x equals 0, or x cubed equals minus 1, i.e. x equals minus 1. Okay, so we know that x equals 0 or x equals minus 1. If x equals 0, then y equals 0, according to this rule here. And if x equals minus 1, then y equals 1. So these are our two critical points, 0, 0, and minus 1, positive 1. Now we need to figure out if we have maximums or minimums here. And in order to do that, we need our 4 partial derivatives, our 4 second partials. So to find fxx, we're going to take the derivative of fx with respect to x. Going term by term, this one goes to 6x. And then this term doesn't have an x in it, so its derivative goes to 0. To find fxy, this means we're going to take a look at fx and take the partial derivative with respect to y. So here fx is here. We're taking the partial derivative with respect to y. So this will become a 0, and this becomes minus 3. So the partial derivative is minus 3. To find fyx, Well, we don't even really need to do any work because we already found fxy. And order of differentiation doesn't matter. So it doesn't matter whether we go fxy or fyx, we'll end up with the same partial derivative. And then lastly, we need to find fyy, the derivative of this thing with respect to y. This term doesn't have any y's in it, so its derivative will be 0. This term, when we take a derivative, we're going to get minus 6y. All right. So altogether, our d function, d of x comma y, is 6x times 6y, or times minus 6y, sorry, minus 3 times minus 3. So if we plug in the point 0, 0, we get that d of 0, 0 is 0 times 0 minus 9 is negative 9. So here d is less than 0. So we have a saddle point at 0, 0, at f of 0, 0. And if we plug in the other value that we found, which is minus 1, 1, we get d of minus 1, 1 is minus 6 times minus 6 minus 9. This is 36 minus 9, which is bigger than 0. And fxx of minus 1, 1 is less than 0. So f of minus 1, 1 is a maximum. All that's left to do now is find the appropriate values. So we found the critical points, we just need to find their output values. And the way we do that is we take a look back at the original function here. So if this is our original function, then f of 0, 0 is 0 cubed minus 3 times 0 minus 0 cubed equals 0. So we can say very confidently that the point 0, 0, 0 is a saddle point. And then lastly, if we plug in f of minus 1, 1, we're going to have minus 1 cubed minus 3 times minus 1 times 1 minus 1 cubed. So this is minus 1 plus 3 minus 1 is 1. So minus 1, 1, 1 is a maximum. And that's finding maximums, minimums of multivariable functions. Thank you so much.